Okay, in today's class, I'm going to talk about a super important chapter. And the reason this chapter is important, because this is the building block of next 3 to 4 lessons. So today we are going to start something called as the gear design. So we are going to start gear design. So how do you design gears? Now, first and foremost, what are gears? Have you seen gears? Any? And so somebody tell me, what is the main application of gear? Transfer torque. Then any, yeah, and increase power. Power is energy. Energy can neither, yeah, energy can neither be created nor be destroyed. It can only change forms. So please note, is gear does not create power. What it does, it changes the characteristics of power. So, and I think I discussed this, but I just want to tell you, gear is used for power transmission. And power transmission P is product of torque multiplied by angular speed. So if you have a gear train, then what you can do is you can change the properties of torque or speed. Okay, so next quiz number 3. Somebody asked this, is it due during the spring break? I did not realize when I put the due date that it falls during the spring break. My suggestion to you would be to finish it off before the spring break so that you can enjoy spring break without any pending items. But for some reason, if you need to turn it in after the spring break, that is okay. First and second quizzes, they are in the process of getting graded, but the grades are not released yet. I spoke with the grader. He's taking a little bit of more time to go through all the FE analysis because there is a lot of material that needs to be graded. So they are being graded. If you are super concerned about your grade, just shoot me an email and I will forward it, or I'll forward it to the grader, and you are welcome to talk to him directly if there are any questions. Okay, so going back to our discussion, power transmission is the product of two terms. One is torque and other one is angular speed. So you have torque and angular speed. Now my question is, what other elements can be used for power transmission? Gear is one. What? Yeah. Belt can be used for power transmission. What else? Pulleys can be used for power transmission. What else can be used for power transmission? Fluid under pressure can be used for power transmission, which means the hydraulic motors, they can be used for power transmission. Now, essentially, I'm going to start with the fundamental element of power transmission. And from there, we would develop something called as the law of gearing, which is the kinematic relationship that has to be followed for any gear train. And then we would derive the equations for gear, and then we will look at the design process for gear. There are different types of gears. There is something called as the spur gear. There is something called as the helical gear. There is something called as worm gear, worm wheel. There is bevel gear. There is double helical gear, which is also called as the herringbone gear. There is spiral bevel gear. So there are lots and lots of gears when it comes to practical applications. However, let me tell you, spur gear design is the fundamental design that prevails through all these different variations of gears. So I'm going to start with a very simple application. So what I have is I have a friction wheel here. So I'm going to replace, for basic analysis, let's try to study two friction wheels. So I have one friction wheel here and I have other friction wheel here. Why they are called as a friction wheel? Because these two wheels are in contact with each other. So clearly there is this big wheel, okay, and I'm gonna call this maybe R big for big wheel, and this is the small wheel that I'm gonna call R small. And clearly, when the big wheel rotates, small wheel is going to rotate. The key question is, why would rotation of big wheel cause small wheel to rotate? Because they are in contact, right? Is that the reason that the small wheel is rotating? Because they are in contact? Let me give you a hypothetical situation. I take lubricant and pour that lubricant in between those two wheels in contact. Now, if I rotate the big wheel, do you think the small wheel will rotate or would it slip? Or perhaps it could stay stationary. It will not rotate at all. So the fundamental element that is causing the gears or the friction wheels to transmit power is friction. That's why they are called friction wheels. So what is the application here? So please understand, when these two gears are in contact, at the point of contact, you have normal reaction. From Newton's third law, every action has equal and opposite reaction. So this is a normal reaction. When you have normal reaction, if the coefficient of friction at the interface is mu is coefficient of friction, you get frictional force. So please try to understand that if this is rotating like this, then what's going to happen is the coefficient of friction will be, say, mu. So there will be something called as normal reaction. So there will be a force mu times n acting over here. And for this equal and opposite mu times n, there will be another force, which is mu times n, that would be acting here. So now what does this mean? If I were to draw the free body diagram, which means I separate out these two gears or friction wheels, I would observe that at the interface, I have a normal reaction, and then I have a coefficient of friction. So I have mu times n, and this is n. If I look at the small friction wheel, same thing, I would have n and I would have mu times n. So please note, these are virtual forces, which means after separating out these two elements that are in contact, I see the forces at the interface. But when I combine these two, these forces cancel each other because they are action and reaction forces pair. Now, another thing which is super duper important that I want you to understand, and that is fundamental to the law of gearing, is I want you to look at this interface. I'm going to call this P. This point P is at the contact and on the line of centers. So this is called as line of center. So LOC. P, it's called as point of contact. And before I even explain law of gearing or anything for that matter, I want to ask you something like this. Do you agree with me that when the power transmission is smooth, which means the big gear is rotating the small gear or big wheel is rotating the small wheel, point of contact, POC, is on line of centers? Let me repeat. Do you agree with me that when the big wheel is rotating the small wheel, then P is going to be on line of centers? Do you agree with me? In other words, that point P is shared by the big wheel and the small wheel at the same time. So that point P can be considered to be on the big wheel as well as on the small wheel. Do you agree with me? In other words, this is super important. Velocity of point P, whether you consider that on the big wheel or on the small wheel, is going to be the same. Since that point P is shared by these two elements, point P cannot break. It cannot have two different velocities. It has to have only one velocity, which means, and this is super important, velocity of point P, whether we consider that on the big wheel or velocity of point P, we consider that on the small wheel, that has to be the same. If it is not the same, that means the material has failed or the material broke or that point P shattered. Do you agree with me? So what does this give me? So if I have omega of big wheel and I have omega of small wheel. So I have omega big and omega small, where omega big is the angular velocity of the big wheel, omega small is the angular velocity of the small wheel. Can I write down equations like this? So I would say velocity of P on the big wheel is radius of big wheel multiplied by omega of big wheel. Do you agree with me? Omega times R. On the small wheel, I would do the same thing. Radius of small wheel multiplied by omega of small wheel. Do you agree with me? Now, what I'm going to do is, I'm going to take the ratio RB divided by RS is equal to WS divided by WB. What does this tell me? This tells me the speed of those wheels are inversely proportional to their radius, which means if the big wheel, so if the big wheel is 4 times greater radius, then your ratio is going to be 4. And this 4 is called as reduction ratio. What that means is the ratio of the speeds between the angular velocity of the big wheel and the angular velocity of the small wheel. So please understand, this is a very, very important equation in the case of friction wheels. Now, let's take a step back. And I need to write this equation and I need to write this statement, and then we'll try to invalidate the statement. So right now, point of contact, which is POC, is on line of centers. POC is on LOC. Now, let me ask you this question. If I pour lubricant, what would happen to point P? Just visualize, if I pour lubricant, what would happen to point P? The velocity of the gear and the velocity of the pinion at the interface is not going to be equal, which means the friction wheels would start slipping. Do you agree with me? Slipping is not a smooth power transmission. When slipping occurs, two things happen. point of contact is not on the line of centers, and velocity of point P on B will not be equal to velocity of point P on S, which means this equation that I have shown over here will no longer be valid when the pair starts slipping. Everyone understood this? Yeah.
If we are considering that both the wheels are linear axle, then how does the point of contact?
Okay. So geometrically, it will not move. Kinematically, it will move. So now there is something that I have to explain. There is a geometry, and ideally we assume that the kinematics is governed by the geometry, but it's not required that the kinematics be constrained by the geometry. Depending upon the operating conditions, depending upon maybe slippage, friction, the kinematic parameters could be different. So what I want to tell you here is that point of contact, POC, is on LOC is required for smooth power transmission. What happens, and this happens all the time, what happens is point of contact is on line of center. Maybe there is some slippage, but still there is some power transmission. If there is slippage, you agree with me, there is heat generated because of the work done by friction, and that heat gets dissipated. So basically the friction wheels get hot and the heat gets dissipated. That's fine. But sometimes, actually, let me emphasize this. Sometimes friction wheels are used in certain mechanism as mechanical clutches. What do I mean by mechanical clutches? So for an example, if you have a big wheel and a small wheel, and the interface has coefficient of friction mu. So what is the power that can be transmitted by that interface? The power transmitted by that interface is going to be mu times n, which is the friction force, multiplied by the relative velocity, which is PV. So I just have to repeat this once again. So let's understand what is the power transmission capacity. And please note, this is power transmission capacity, which is mu times n, which is the frictional force multiplied by velocity of P. So this is the frictional force multiplied by the velocity of point P. This is the power transmission capacity of the interface. Sometimes what you want is you want these friction wheels to slip if there is huge demand, huge power demand that would ruin the transmission. So for an example, think about it like an internal combustion engine is connected to pump, and all of a sudden pump that was pumping clear water starts, for some reason, the clear water gets contaminated by mud, and now it's like a slurry. It's like mud that pump is pumping. Clearly, the amount of power and the torque that is needed to pump the mud is much, much greater than the power required to pump the water. So, and clearly, if the pump starts pumping mud, it's going to get damaged. If you don't believe me, put mud in your washer and tell me what happens. After some time, the washer would break down. Worst even, put some concrete in your washer and see that washer would break down after a couple of cycles. Exactly the same thing is going to happen with the pump, either reciprocating or rotary. Pumps are for fluids. Pumps are for liquids. Pumps are not for semi-liquids or basically contaminated stuff. That there are the design process for pumping contaminated water or wastewater, that is called as black water or blue water, is completely different. Anyway, that being said, so when that pumps pump starts pumping dirty water, clearly the power required by that pump is going to exceed. We don't want to happen. At that time, we want pump to stop. How would you stop it? Either you can have a mechanical fuse, like basically maybe monitor the current drawn by pump, monitor the voltage by the pump, and if it exceeds, you have a fuse, that fuse goes out. That's an electrical way of handling that case. Alternatively, you can ensure at that interface that the power transmission capacity is mu n times Vp, and if the power required by the pump exceeds this capacity, if the power required by the pump exceeds this capacity, then there will be automatic slippage of the interface. So that is mechanical fuse in the power transmission system. Something similar is done with the clutches, mechanical clutches. So basically you can set a threshold power for the mechanical clutch. And if the power transmission requirement exceeds the frictional torque transmission capability of the clutch, the power transmission starts slipping. So these are some mechanical design tricks that you can certainly play. One important thing that I want to tell you is, for smooth power transmission, point of contact has to be on the line of center. This is called as the fundamental law of gearing. And I'm going to write this down, which is super duper important. So this is called as the law of gearing. For smooth and continuous power transmission, point of contact must be on line of centers. Now, as you can see, that unfortunately, potential for slipping is very high if you have two friction wheels. Now, let me ask you this question, and let's start with, say, you have maybe a belt drive, okay? Why don't we use belt drive in bikes? What type of power transmission we use in bikes? Chain. So now my question to you is, why not to use belt drive in bikes? Yeah. Nope. 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 You can add tensioner and increase the tension. So well, belts are used in serpentine and in serpentine belts, right? So why not use belt? So the reason for that, online, any suggestions, answers? So here is the fundamental reason. There are two types of commonly used belts. One is called as V belt, and the other one is called flat belt. So, and then there is a timing belt, but that comes a little bit later because it combines some aspects of gearing. But V belt and flat belt, they are not positive power transmission devices, which means they can slip. Imagine you are using a V belt or a flat belt in your bike and you start going uphill. So you'll come to a point where the belt drive, rather than transmitting the torque from the pedals to the wheel, it would just spin and the bike will not go up. As a matter of fact, it will come down the hill. Can you visualize the situation? Because belt drives are not positive power transmission elements. Chain drives are. So in chain drives, what you have is you have sprockets. And then because of that, you ensure that if you are applying torque at the pedal, some torque, depending upon the design, will be applied at the wheel. So chain drives are positive power transmission elements. What are the disadvantages of chain drive? So problem with chain drives is even though they are positive transmission elements, they are not as forgiving as belt drives. So which means you have to have accurate center distance. You cannot have sprockets out of alignment. So if you have a minor misalignment between the sprockets, after some time, the chain would just fly off. Have you seen that happening? The chain just flies off. So belt drives are more forgiving because basically they can deform. And, and there are design philosophies. So for an example, people started saying, yeah, belt drives are forgiving. Chain drives, basically, they are positive power transmission. So how do we combine best of these both worlds? And they came up with a timing belt. So if you look at the timing belt, basically timing belt has teeth, which means it's like a positive power transmission device. At the same time, because of the compliance of the belt, it's forgiving to the misalignments or maybe minute stretches or some, and again, basically there is a hysteresis also. So all that stuff. But then the problem with that is belts do not last forever. Chains, on the other hand, they can last forever as long as they are maintained well. So then there is this design philosophy. Should I go with a belt drive or timing belt, or should I go with a timing chain? So probably, Hondas and Acuras, they adopt this timing belt philosophy, wherein they say that that's okay. We want to make sure that our transmission is forgiving to the the misalignment. So we are going to use the belt drives. On the other hand, if you look at Nissan, they say no, we don't want our customers to change the timing belt after 100,000 miles. So we are going to use chain drive. So once that chain drive is in place, basically it's continuously dipped in oil, then it will go forever. So those are different philosophies. Timing belts in the case of Honda, because Honda uses interference engine. So basically that goes with the engine design, so that you have a timing belt. But that gives you another problem, that if timing belt fails, then the engine, the piston slams on the valve body, and basically you will have to rebuild the entire engine. So if you have a timing belt, please get it replaced at the manufacturer said intervals. So coming back to the gear transmission that we are talking about, I want positive power transmission. Do you agree with me? Friction wheels is not a positive power transmission. Slipping is possible. So how would I make this non-positive power transmission to a positive power transmission? Cut teeth. Do you agree with me? So what I do is I basically cut teeth here. So I'm going to show you. So again, to start with, we have this big wheel. We have this big wheel. And we have this small wheel. And at the interface, what I'm going to do is, fundamental principle remains the same. So what I have is I'm cutting teeth, and these teeth engage and disengage at the point of contact. So this is how the gear transmission takes place. Now, one thing that is super important. What happens is, because of the unique shape of the gear. So if you look at the gear looks something like this. So gear looks something like this. So because of the shape of the gear, the friction force, the force that is causing uh, the, the transmission to work is basically the force that is transmitted from the big gear to small gear is not going to be perpendicular to the line of centers. So I want to emphasize this. So please understand, this force is perpendicular to the line of centers. But in the case of gears, because of the shape of the gear or the gear profile, this force will be at an angle. So this force will be at an angle. And this angle is called as the pressure angle. This is called as the pressure angle. So what is the pressure angle? In the case of friction wheels, the force that is transmitted is going to be perpendicular to the line of centers. But in the case of gears, the force is always at an angle. And typically, this pressure angle is designed to be 14.5 degrees to 20 and 21 degrees. So these are the common pressure angles. Now, what about the gear profile? So please try to understand, if you look at the gear has this particular type of shape. So this is an interesting shape. And clearly the question is, why is this shape needed? So why is this particular shape? And for that, I want you to do this thought exercise. And if you can actually try doing this. So what I'm going to do is, rather than this weird shape of the tooth, I'm going to cut, say, rectangular teeth. So for an example, I have this big gear. So let me see, I have this big gear and I have this small gear. And what I'm going to do is, I'm going to cut rectangular teeth. So I'm going to cut rectangular teeth. So no weird shape, no curvature. So pure rectangular teeth. Now my question to you is, if I have two rectangular teeth, one on the pinion and one on the gear, come in contact, would there be any power transmission, or would they would lock? Can you visualize that they would just lock? Well, that's true, but okay, let's say that you have short gears. No. I completely understand, and that's totally fine. They're basically, if they have short gears, it kind of works like a friction wheel. So now, basically, imagine that you have those rectangular teeth, but they are made with soft material, which means those two teeth, when they come in contact, if they want to cut each other, they can cut each other. Now, can you see that? I mean, I want you to think about this actual assembly. So these two gears come in contact and they start scraping each other out. And don't you agree with me that rectangular flat shape would eventually be converted into sort of this curved shape? Can you visualize that happening? And why would that happen? That happens because if you look at the way the point of contact, so this is very super important, so please pay attention. If you visualize the way the point of contact is moving on the surface of the gear, please understand, if you visualize the way the point of contact is moving from the surface of the gear, it's not staying fixed at one point, it's going back and forth. So it's going from the tip of the tooth to the root of the tooth. So basically it's going forward and backward. And kinematically, for this smooth forward and backward motion, it is something like a cycloid, or basically is like an involute. So there are two types of profile. So I would show you both. So think about that. This is a circle. On there, you have this flat surface. And what's going to happen is, if this circle rolls on this flat surface, if this circle rolls on the flat surface, the point is going to trace a curve. The point is going to trace a curve, and that curve basically is nothing but the involute curve. So in other words, what you can do is you can actually roll this line back and forth onto this circle, and the point that is traced by that line is nothing but the involute. So the gear can be cut with the involute profile, because involute profile would allow proper engagement and disengagement of teeth. Please note, here is something super duper important. I'm studying the contact between the line and the circle. I'm presenting here the contact between the line and the circle. Two gears, when they come in contact, it's like circle to circle contact. It's not line to circle contact, but line to circle contact is better approximation. So the profile of the gear, or the curve, the gear curve, this is actually called as involute profile. This is involute. This is involute. And the gears could have an involute profile, or they could have a cycloidal profile. What is a cycloidal profile? Cycloidal profile is, rather than tracing the point P on the line, which is rolling on the circle. So involute profile is constructed by tracing a point P on that line. That line actually rolls on the circle. Ideally, you have gears which are two circles rolling on top of each other. If you were to trace the point P on the small or the big circle, you would also get a curved profile. You'll get a profile, and that profile is called as the cycloidal profile. So cycloidal profile is the ideal profile for gear transmission, because basically the two gears coming in contact, disengaging, that is like basically one small wheel rolling on the big wheel. But at the bare minimum, you can actually assume an involute profile and then have a line roll on the circle, and that point, so basically that curve that is traced by the point on the line is nothing but the profile of the gear. So quick sort of summary. Gears could have two different types of pressure angles. Gears can be cut at 14.5 degrees of pressure angle. Gears can be cut at 20 degrees of pressure, 21 degrees of pressure angle. Gear profile could be involute, or gear profile could be cycloid. Involute profiles are easy to cut. Involute gears are cheaper. They can be easily cut. Cycloidal gears are expensive to cut. But please understand, the wear in the involute gear is more, because that is an approximation of the contact. Wear in the cycloidal gears is less. So basically, the noise from the cycloidal gear train is less compared to the noise from the involute gear train. Where do we use involute gear train, and where do we use cycloidal gear train? Involute gears are commonly used for all the applications like automotive, power transmission. Cycloidal gear trains are used in specialty applications, wherein you want less heat generated, you want power transmission, you want to have very less noise, and basically where you have some critical measurement or specialty equipment that have certain restrictions. So most commonly, involute profiles are used in gear cutting. Okay. Now there is something called as full gear and there is something called as the stub gear. So what is a full gear? So full gear means what you have is you have gear, something like this. So you design the gear and purchase the gear, and this is the gear. Stub gear, which means usually the top part is shaved. So stub gear is like a stub. So top part is removed. There are certain applications for the stub gears. For example, as it was mentioned, that if the tooth height is small, you can actually control basically the center distance more accurately, and that is where you use the stub gears. And there are certain applications wherein the center distance control is more critical. So at that time, what you do is you just shave the top of the gear, and that actually becomes the stub gear. Now, what are the different types of gears? And please understand, this part is super important. So what is the motivation behind me teaching gear design? Because few years ago, our students graduated and then they interviewed, and at that time they were shown two different types of gears, and they were asked what do you call, what is the difference between those two gears and what are their applications. So they couldn't answer, and then they came to me and they kind of drew the picture and then they showed me what was asked. So one was a spur gear and other one was the helical gear, and their applications, advantages, disadvantages is completely different. And as a mechanical engineer, you should have a thorough understanding of power transmission elements, because please understand, gears are everywhere, from your cars, bikes, power transmission elements, basically the 3D printers, motors, gearboxes, everywhere you're gonna see gears. They could be metallic gears, they could be nylon gears, they could be plastic gears, but the gears are going to be there. So what are the fundamental types of gears? So depending upon how the axes of the input shaft and the output shaft are oriented. So let's look at if these two shafts are parallel. So for an example, if the input shaft is parallel to the output shaft, then if you look at from the top, the gear train is going to look like this. And if you look at the gears, if the gears are cut parallel, so this is like this. If gears are cut parallel, and if you look at the side view, it's going to look something like this. So something like this. So basically all these faces are going to parallel to each other. This is called as the spur gear. Spur gear is a very fundamental gear. So this is spur gear, which means the gears basically are, if you look at the face of the gear, it's parallel to the line to the axis. So basically you have the input shaft and you have the output shaft, but these two shafts are parallel to each other. So this is the spur gear. Now sometimes what happens is the face or the top part is not parallel, but it is at certain angle. So let me show you how does that look like. So for an example, you have the gear and say you have a pinion. Again, the shafts are parallel to each other, but the teeth are cut slanted. So in that case, what you have So basically, this is how the gear looks like. And then you will notice that they are at an angle. So rather than, and what I can do is next time you can just take uh, or just watch some pictures of helical gears and spur gears. This gear is called as helical gear. And why is this called as helical gear? It is called as the helical gear because there is an angle at which the gear face is cut. And this is basically the helix angle. So this is the helix angle. So helical gear has a pressure angle and also has a helix angle. Now, why do we need helical gear? The clear advantage of helical gear is, think about it like this is the face width, okay? And this is the face width of the helical gear. For the same face width, the amount of tooth material helical gear has is more than the amount of tooth material that the spur gear has. In other words, for the same footprint, helical gear can transmit more power. Can you see that the helical gear is like slanted? Spur gear is parallel. So amount of tooth material that the spur gear has is less to the helical gear. That means helical gear is stronger than the spur gear, which means for the same size, helical gear can transmit more power. Everyone understood this? Now, what is the disadvantage of helical gear? Now, please understand, since the helical gear is at as a helix angle, spur gear does not give you any axial force. Spur gear does not give you any axial force, but since the helical gear is at an angle, you are going to have a component of force that is in the axial direction. So which means when you are going to design the helical gear, by default, you have to use a thrust bearing so that that axial force is taken by thrust bearing. For spur gears, you do not need a thrust bearing, but for helical gears, you need a thrust bearing. Now, is that bad? No. In certain cases, you want to make sure that there is axial thrust. And that is the reason why, if you look at the stick shift cars, the cars, manual transmission cars, the last stage is usually a helical gear, so that there is a positive thrust on the clutch plate all the time. So because of the gear geometry, the helical gear will continue to add thrust to the clutch plate that would ensure that the clutch plate is in positive contact from the input side to the output side. So helical gears are used when you need that constant thrust to be present. Spur gears are commonly used for power transmission, but they do not give you the thrust. Now, what happens if your power, the input to output shafts are not parallel to each other, but they are at an angle? So what you use is something called as the bevel gear. So basically, this is how the bevel gear looks like. So basically, these two shafts and bevel gear, if they are of the same size and they are perpendicular to each other, then it is called as mitter gear, M-I-T-T-E-R, mitter gear. So this is called as the bevel gear. And they don't have to be at perpendicular. They can be at some other angle as well. So you have the bevel gear. So bevel gear are used when the power transmission shafts input and output, they are not parallel, but they are at an angle. The angle could be 90 degrees, angle could be 45 degrees, angle could be 60 degrees. Now, next part is what happens is, but here is one thing. Please note, the spur gear, bevel gear, and helical gear if you visualize that you have a plane that is going to the center line of the shafts, the shaft center lines in one plane. Can you visualize that? That the shaft center line. So this is center line 1, center line 2, center line 3, center line 4, center line 5, and center line 6. Can you see that these center lines are in one plane? What happens if the shafts are not, center lines are not in one plane? In that case, what you do is you use worm gear. So basically you use worm wheel. So this is worm and you have worm wheel. So this is wheel and this is worm. So basically you rotate, this is the shaft center line and the other center line is somewhere over here. So these two center lines are perpendicular to each other. Please note, in the case of bevel gear, the center lines are perpendicular to each other. In the case of worm wheel, the center lines are perpendicular to each other. But in the case of bevel gear, the center lines are in one plane. In the case of worm wheel, the center lines are not in one plane. Can you see that their planes are perpendicular to each other? So these are some of the gears that we are going to study when we actually going to study the gear design. So we are going to start with the spur gear design. Then we are going to extend to the helical gear design. Then we are going to study the bevel gear design. And then we are going to study the worm wheel design. Now, what are the classic applications of worm wheel? Please understand, spur gear, helical gear, or bevel gear is bidirectional, which means if you rotate the input shaft, output shaft will rotate. If you rotate the output shaft, input shaft will rotate. Can you see that? However, worm wheel is not bidirectional, which means if you rotate the worm, wheel would rotate. If you rotate the worm clockwise or counterclockwise, the wheel would rotate clockwise or counterclockwise. But if you rotate the wheel, worm is not going to rotate. Do you agree with me? Are you with me so far? So which means if you rotate that big wheel, the worm is not going to rotate. That's a good thing and a bad thing. When is it a good thing? Say for an example, if you want to use worm wheel, which is the classic application as the hoist mechanism. Say like this whole thing needs to lift. So it needs lifting people. So and all of a sudden, and here there is motor. And here there is motor. And all of a sudden, power gets lost. No power to the motor. The wheel would get locked. So the load will not overrun under gravity. So it typically in hoisting mechanisms, worm wheels are used. The problem with worm wheel is the efficiency of power transmission. So people usually say the worm wheels are not efficient, and that's absolutely correct. Worm wheels are not as efficient in power transmission. But then now you have recirculating ball screws design, wherein what you have is where the wheel comes in contact with worm, you have recirculating balls that actually minimize the friction that make that power transmission more efficient. So in the case of and these are used in lots and lots of applications. Typically worm wheel are used when you need significant reduction, more than 10 or 12, 15 reduction ratio, because as you can see that worm can rotate at a very high speed, but still the wheel would rotate slowly. So if you are connecting worm to a motor, rotate the worm at very high speed. But if you want wheel to rotate at very slow speed, what that means is torque on the wheel is going to be significantly higher than on the torque on the worm. Because please understand, power is transmitted from worm to wheel. Power is transmitted from worm to wheel. Worm will have low torque, high speed, but the wheel would have low speed, which means you will have high torque. Everyone understood this? So those are some of the applications of worm wheel, Bevel Gear, Spur Gear, Helical Gear. But what I want to give you an example is, imagine if the radius of the gear is infinite. If the radius of the gear is infinite, what it means is you have this small gear, means small pinion, and what you have is the big gear has that infinite radius. So what you have is you have rack and pinion. So rack and pinion, which simply means that your gear, the radius of the gear is infinity. And then you have the power transmission going forward and backward. So your steering wheel, the car steering wheel, usually has a steering wheel and steering rack and pinion. And many a times it is accompanied by power steering. So you have a hydraulic cylinder that actually assists rotating that steering rack. But essentially what you have is you have a rack and pinion assembly in your steering wheel. And designing rack and pinion is similar to the spur gear design. Everyone understood the gears, types of gears? Yeah.
I just have a question about lubrication on some of the gears.
Yeah.
Is it for reducing the heat that is acquired through the friction of two gears coming in contact? Like in cars, right? If you don't have oil in your car, it seizes. Is that because of heat or?
So lubrication, basically there is an entire field. So it is a long answer to a short question, but this is important because I believe that you should be aware of these concepts. So there is an entire field of friction, wear, and lubrication. Friction, wear, and lubrication. And that field is called as tribology. So tribology studies friction, wear, and lubrication. So what is the purpose of oil in the automotive power transmission? So, let's take a step back. You have engine has some oil. You have you have transmission has some oil. So what does oil do? Oil does a lot of stuff. Oil reduces the friction coefficient. Oil cleans the gear surface, because believe it or not, after few years or thousands of miles, there is going to be some teeny tiny microscopic pitting on the gear. And basically that's why what you have is you have oil filter that basically filter the oil and recirculate the oil. Many a times, not in the engine, but have you noticed that there are sealed transmissions? So your cars would have sealed transmission. In that particular case, that oil basically holds the gear assembly together, because basically when you have a sealed transmission, you don't replace the oil. So the life of oil is greater than the life of transmission. So depending upon what your uh, engineering requirements are, oil can be used for cleaning of the interface, uh, cooling down, then reducing the frictional coefficient, and cleaning the point surface. And if you really want to see how does oil work, you should sometimes see the timing chain of your engine. If you take out the front cover that is on your engine and open up the, depending upon your engine design, you should be able to see the timing chain on the gear. So if you see the camshaft, you'll see the timing chain. That timing chain is continuously submerged in oil bath. And the reason for that is that actually extends the life of the timing chain. because of that, the timing chain is cooled, timing chain is cleaned, the coefficient of friction is reduced, and that basically allows the timing chains to go up to 100, 150, 200,000 miles without any problem. So the purpose is, depending upon what you desire, the lubrication can perform cleaning, reducing the amount of friction, reducing the heat. Sometimes the lubricating oil would transfer the heat. So in the case of, for an example, automotive transmissions, if you notice, the transmission, basically the transmission oil runs through the part of the radiator, that is where the transmission oil is cooled. And basically that cool transmission oil is fed back into the transmission. So oil would dissipate the heat as well. Now, some of you may ask me, why is dissipation, external dissipation needed? Because please try to understand, if you do not have a radiator on oil cooler or anything like that, then if the oil is just sitting there, the amount of surface that the oil has to dissipate the heat is restricted. So because it would be just because free convection. So, but if you circulate the oil through a heat exchanger like radiator, and you add force convection to it like a fan, then you can cool the same amount of oil much quickly, much efficiently. That would extend the life of the oil, that would extend the life of the transmission. So that's why usually you have oil coolers in engines, wherein, and those oil coolers sit in somewhere where the radiator fluid is flowing to the engine, basically water jacket. So those are the more important applications of lubrication. And what we will do is, sometimes in one of these gear designs, one of the gear design exercise is not to design the gear, but to design the housing. So when we will talk about the spur gear design or helical gear design, I'll take an example wherein you design the gear train, you design the housing, and then at that time, I would go ahead and tell you how to select the oil for that particular power transmission. Because please understand, oil is a two-edged sword, and people don't like it to hear it, but this is what it is. If the oil is too viscous, rather than decreasing the coefficient of friction, it increases the coefficient of friction. In other words, it increases the power that is needed to transmit. If the oil is very less, if viscosity is too low, it does not retain the oily layer on the point of contact. So what you want as engineer is, you want a thin layer of oil, not thick. A thick oil layer does not help. You just need a thin oil layer at the point of contact, so that the pressure from the tooth to other tooth is taken up by that oil layer. And when you design the oil, if different types of oil has different properties of contact pressure. So basically, when you select the oil, some oils can support very high contact pressure. Some oils can support not so high contact pressure, but they are better dissipation of heat. So what you have to do is, you have to basically balance these factors together and finally come with that oil grade. And again, the temperature affects the viscosity. So sometimes you use a different SAE grade in summer, sometimes you use a different SAE grade in winter. We don't do that in Arizona, but if you are in Midwest, basically where the summers are brutal, summers are high, winters are very low, then you will have to use two different grades of oil for your engines. Okay, question? Question?
I was going to ask, is that where the pressure the oil can withstand? Is that where the weight of it is? Like 15W30?
No, 15W30 is basically it. So I will actually discuss this, how that numbering system is assigned. But 15W30 depends upon the viscosity, the range where that viscosity is maintained, and its applicability. So again, this again depends upon the viscosity, and you have to be super duper careful with the viscosity. You don't want oil that is too viscous. Too viscous oil would increase the power transmission losses. If oil is very less viscous, it will not maintain the film where the point of contact is occurring. So it will not help you with the lubrication. So you would want to have some sort of optimal viscosity, and that comes from something called as the Zn by P type of ratio. So there is, I will talk about this in next class, like when you select the lubrication, what to look for. And when we design a gearbox, first we will finish the design of gear. I will talk about the nomenclature of gear, what are the parameters that are used in gear design. Then I'll walk you through a gear design recipe, and then I will work out one or two problems for gear design. And then we would do a gearbox design, where we will design the gear, we will design the housing, we will find out what is the heat dissipation capacity of the housing. Does it need external some type of radiator or coolant? And then we will try to find out what type of lubricant we should use for power transmission. And at that time, I will talk about the basic concept of tribology, basic wear friction mechanisms, and what type of lubricant would be good for what type of application. So I'm going to stop here. So now the class is going to go like, I'm going to do the gear designs, and all these gears are used in engine and power transmission. So once we are done with gear design, the next natural progression is design an internal combustion engine from scratch. So basically design the cylinder, design the piston, design the connecting rod, design the camshaft, design the crankshaft, design the valve follower mechanism, and then identify and then do the CADing, and then find the profile for valve opening and closing. We'll just use single profile, not like IV Tech Honda engines where there are two different profiles, one at low speed and one at high speed. We just use a single cylinder engine design. And at the end, what I want to do is, there is a software which is called Lotus Engine Simulation. That software will allow you to simulate and build a single cylinder engine. So I will walk you through that engine design software, and then it will all come together. And then we will study the remaining topics like clutches and pulleys and flywheels and all that type of stuff. So there is a lot more information coming your way. So the lessons are going to be more interesting and more and more important. So I'm going to stop recording.